Hey guys, it's Eric here. I wanted to talk to you guys about DC motor some more, and in particular counter EMF. And related to counter EMF, how do we overspeed or underspeed a motor? When we're talking about overspeed and underspeed, overspeed is always running the motor at over its nameplate speed, and underspeed is running the motor at less than the nameplate speed. Now, the way we underspeed a motor is we reduce the applied voltage to the armature. If you recall, I'll draw it again here, that the motor will always tend to run at a point where the applied voltage is, or at least the counter EMF is close to the applied voltage. So if I draw my little graph here, if you recall, this side of the graph was the voltage, and this side of the graph is the RPM of the motor. And we had an applied voltage that was a fixed value, and it was just sitting up here somewhere. There's the applied voltage. And we have a counter EMF voltage that's produced within the motor, and at 0 RPM it was 0, and at at some point the counter EMF line would be equal to the applied voltage, and we talk about the fact that this motor will always tend to run close to where they meet. And so this motor would be running under these conditions, maybe somewhere around right around there. Now, the way we underspeed a motor or slow a motor down to less than its nameplate value is we reduce the applied voltage to the armature. The reason this motor will slow down when I reduce the armature voltage is because I'm taking this voltage here and reducing it. And so let's say I reduced it to here somewhere. What you can see here is that the motor will now start to want to run at a new place just before where the counter EMF equals the applied voltage. If I continue to reduce the applied voltage, you can see that the motor RPM will also be reduced. The beautiful thing about this is that in all three of these examples, the net armature voltage is the same, regardless of at what speed I'm running the motor. So because the armature voltage is the same at all these three different speeds, the armature's ability to produce torque is also the same at all these different speeds. So a DC motor is really a constant torque motor because in all three of these examples, the armature voltage is the same, and therefore the armature current is the same, and therefore its ability to produce torque is the same. So when we want to reduce the speed of a DC motor, all we have to do is reduce the armature voltage to do it. It will always want to run at some point close to where the motor's counter EMF is equal to the motor's applied voltage. Now, the other thing I want to talk to you about is how do we overspeed a motor. Overspeeding a motor is getting the motor to run at an RPM that exceeds its nameplate RPM. Now, I'm going to draw the chart again. You're probably getting sick of me drawing this, but it's all explained by counter EMF, so I have to keep drawing this counter EMF chart here. And this is the voltage again, and here's the RPM. Now, in order to overspeed a motor, what we're actually going to do is reduce its field voltage. So here we go again. Here's our armature applied voltage. Now with a full strength field, as you are aware, we would have a line like this, which represents our CEMF. And if the applied voltage to the armature is at full strength and the field is also at full strength, this thing will tend to want to run right here. But what happens when I reduce the field current is the motor starts to have a difficult time producing counter EMF. Remember that counter EMF is the voltage that's induced into the armature windings because it's spinning through a magnetic field. If I reduce the strength of that magnetic field, the motor actually has to run faster in order to produce the same amount of counter EMF. So with a weakened field, what actually happens is this counter EMF line becomes less shallow, or less steep. So it might start to look like this. And now, if I've reduced the strength of the field, the motor current would certainly start to increase because the net armature voltage has increased. It would start to spin up and it would start to try to run again where the counter EMF is close to the applied voltage. So now here's my new RPM that it's running with a weakened field. If I continue to weaken the field, it becomes even harder to produce counter EMF and it'll want to start to run way down up here somewhere.